need to think about this problem. So let's see, which answer is it? Well, to start, I will tell you that in the title, this is an AP question. So I actually took this from an AP test. And it's a little bit of a tricky one, but it really gets at the heart of what we've been doing. So what I want to show you here is they're asking us to figure out this integral. However, we know the integral from a to b of f of x dx. So we know this, right? That is the area under the curve of f of x is equal to a plus 2b. Well, I have f of x here, but there's an extra 5. So the very first thing I'm going to do is I'm going to split up this integral using the property of integrals. And I'm just going to rewrite it as two separate pieces. Now, the reason why we're going to do that is because we know what f of x from a to b is, right? The integral from a to b of f of x dx is equal to a plus 2b. So I already have that answer. So I know this whole piece is a plus 2b. And then the second part is now I just have to evaluate this integral using the antiderivative. So I'm thinking, whose derivative gives me 5? Well, that's 5x. And then we're going to evaluate 5x from a to b. And maybe I should put brackets around this so we know we're not including the blue part. But what do? We take the upper bound minus the lower bound, and then we include the two values from before, combined like terms. So I've got 2b plus 5b, that's 7b. And I've got 1a minus 5a, so that's 4a minus 4a. And the correct answer is C. So I think it was 6 of us got that. All right. I just wanted to show you this kind of problem because it's a perfect style of AP question that gets really at the heart of two things. Do you know the properties of integrals? That's what this one says, right? Split it up. And then, do you know what the given information means and how you use it? But also, do you know how, if you have a constant or any other value, to take the antiderivative? And now we're just dealing with letters instead of numbers. Okay, so hopefully you had a chance to check your grade. I'm going to take a moment here to talk about third trimester and the AP exam. And I know we went over that a little bit in detail last week. I want to just hit home a couple other points here quick. Okay, so in general, what have we been doing? Well, Unit 6, we just took a chapter test on Part 1 of Unit 6, and now we're finishing Unit 6 with just 2 small units. And the focus on this small chapter or section is techniques for integration, right? How do we do integrals? Well, this is things that we've already done. We had that chart that says, if you know the fact, here it is. Just take the antiderivative. That's really the fundamental theorem of calculus. Then we spent a good amount of time on U substitution, and we're going to do more of that today. Okay? But if those don't work, and actually we probably should flip the order of these, algebra, right? What if we couldn't use the chart, then we said, could algebra help us out? We could factor or divide things out to make it easier, and then we could do the antiderivative. But these 3 pieces are kind of a checklist of you should be comfortable doing integrals using any one of these 3. But the question today is, what if it doesn't work? If one of these don't work, then we have 2 other options that we're going to explore today: long division and completing the square. So these are the new techniques for today. You don't really have to write this. If you do want this, all of these notes will be available online right after class. So, all right, hopefully you took a screenshot at some point, or you have this page bookmarked in your text. Page 439 is just the integral rules. Well, today we're going to be looking a little bit at the inverse sine and the inverse tangent. Okay? So if we see 1 over 1 plus x squared, we know that that antiderivative is tangent inverse of x plus c. So we're going to focus on kind of these two last pieces. I should mention we're also going to do the 1 over x, which is ln. That's a big one. That one always comes up. So we're going to do this one as well. Okay. I don't want you to write this part. I just wanted to make you aware of a pattern. So look at all of these integrals. They're all close to being the same thing, right? I have a fraction. Now sometimes there's a constant or an extra function in there. But notice all of the denominators are linear. And that's kind of a big piece. If you have a linear model in the bottom of a fraction, watch just this pattern here. And again, I don't expect you to write this, but what do? We split this up into two separate integrals. The 4 is a constant, so I'm just going to float that out. And then we can solve this one very quickly, right? Whose derivative gives me 3? That's 3x. So this piece is very friendly. But this piece right here is going to occur very often. All right, so I have 1 over x plus 1, or x plus 2. Well, what if I do u substitution here? And I take the bottom and let it equal x plus 2. And then I take the derivative of that. Notice the x turns into dx and the 2 goes away because it's a linear model. So you're always going to be left with dx. Maybe there's a constant there, but not in this case. And then when I do u substitution, it becomes 1 over u, which is ln of u. And then we just plug u back in. So what if I had this piece right here? And notice it's almost the same work. The 2x splits off, the 5 is a constant, so it floats out, and now I have the linear model just like I did underneath here, which is going to be my u value. And because it's linear, all that's left when you take the derivative is dx. And when I do u substitution then, it's 1 over u, which is the same portion right here. So we get the natural log of u appearing, and then we just plug u back in. Okay, this one is almost the same. It's slightly different because of the 2. And watch how the 2 has a different effect than just an x plus 2 or an x minus 3. So first thing we would do is move that 7, the negative 7 out, because I want this 1 over something. And then we're going to let the u equal 2x minus 4. But notice now when I take the derivative, the 2 is present, and I don't have an extra 2 here, so we do have to move that 2 over with the du. That's the only thing that makes this problem different than these. So then what do? We place the bottom with u. Du becomes 1/2 du, and now we can take the antiderivative. Okay, so what do? We get the natural log of u, which we know what u is. So notice how these are almost the similar format. The only thing that really makes them different are the numbers out in front or the u inside. But they're all natural log pieces. And that is going to come up today. So I just wanted to show you that without taking a ton of time. Okay, well, first thing, I want to make sure you guys have a little bit of feedback. Consider this a review for the test on Thursday this week. Okay? I want you guys to evaluate. We're going to give you about 12 minutes on this. So we'll come back at 8:45. That's 13 minutes, but I want you to try each one of these values. Okay, evaluate each integral. Okay, so let's go over these problems. What I did was I actually pre-wrote them out so we could go over them a little faster, just so you could get some feedback. Remember, this is a really good quick test of do you know u substitution and how to do u substitution with your limits. So let's go over the first one here quick. Let's see if I can break this down into pieces. The first question is, how do we know what to pick? Do I pick the sine or cosine? Well, when I look at this, cosine, the 2 minus cosine of t is inside of the 2, the power of 2. So remember, u substitution is what we use to undo the chain rule. And when we're looking at the chain rule, that was a function inside of a function. So we want to pick that one as my u. And another reason why is when I take the derivative of that, I get a positive sine dt. And notice, here's the sine and here's the dt. The only things that are not taken care of by the u substitution is the 3, but that's a constant, and then the squared. So what we're going to do then is we're going to actually replace cosine 2 minus cosine of t with u. Notice the 3 floats out because that's a constant multiplier. So I have u squared, and then I put du. Now you could write a 1 here and put the du on the side. I actually prefer to do that. But then I have to take the antiderivative. Well, when I have u squared in the denominator, that doesn't help me as much as writing it as u to the negative 2. Now notice the integral symbol still stands because I didn't do any calculus. I just rewrote this as u to the negative 2. And now I'm going to take the antiderivative by adding 1 up here, so I get a negative 1. But if I put a negative 1 up top, I have to divide by a negative 1. And don't forget about the 3 as your multiplier. So then I get negative 3 times u to the negative first power. Well, instead of u, we know exactly what u is. So we're just going to go back and replace it. And if you have this answer right here, that's perfect. If it was a multiple choice question, it would probably be written this way because the negative 1 brings 2 minus cosine t in the denominator. Okay. All right, the next one is basically the same thing, except for now we have bounds. You'll notice we have an inside function, so that value is going to be my u. So I'm going to let x squared minus 2 be the u value. Now, how do I know that that's the right u value? When I take the derivative of that, see how there's an x and a dx left over, and I have the x and the dx as part of my problem? The only thing that isn't present is this 2, which that's just a multiplier. So I can move the 2 over to the other side and get 1/2 du equals x dx. Now, I'll talk about changing the bounds in a second, but when I replace that, you can see the u goes here, the 1/2 and the du are replacing the x and the dx. So the only thing then we have to worry about is my original bounds were written in terms of x. So what do? We take the u value and we plug in x equals 1 and we change the bounds. So I get negative 1 as my new upper bound, and the lower bound we plug in 0 here. 0 squared minus 2 is negative 2. And the nice thing about this is once you change the bounds, you don't ever have to go back to the x's because our goal is to just get an answer here, right? We want to get an answer for the integral from 0 to 1. So I'm going to take the antiderivative of e to the u, which is just e to the u. Notice the 1/2 is the multiplier. And then I'm going to just evaluate at negative 1 and at 2. So you could write your answer like this: 1/2 times the quantity e to the negative 1 minus e to the negative 2. Or you could distribute the 1/2 and write it this way. And that's about as far as I would go. I wouldn't try to combine the fractions because you could do that, but it would get a little messy, and I don't think it's worth doing any extra algebra. Okay? And again, these answers will be posted online, so you can go back and check your work. So let's look at this one now. Now this one's a little bit tricky. I usually, when I first see a fraction, I think, oh, well, maybe the bottom is the u value. But if I take the derivative of the bottom, I do not get the original top. Also notice that this x to the 1/3 minus 4 is inside of the 5th power. So that's my inner function, which is most likely the u value that I want. When I take the derivative of that, now this is where you got to be tricky, or you got to be careful. I have an extra 1/3 that comes down when I take the derivative. That 1/3 is not present here, so I'm just moving the 3 over. So that's where this 3 came from. But notice this right here. X to the negative 2/3 is the exact same thing as dividing by an x to the negative 2/3. So this x to the negative 2/3 is going to replace the negative, or the x to the 2/3 that's in the denominator. All right, and then dx is also going to be replaced. So these two green spots are going to be replaced by 3 du. And we put the 3 on the outside because that's a multiplier. The du is at the end. And then if I replace u, notice I did one extra thing. This 6 is a multiplier. It's a 1 over 6, so I pulled that out. So then I get 1/6 times 3 is 1/2. And then evaluating u to the 5th, we add 1 to get u to the 6th. And then if I put a 6 up top, I have to put a 6 out in front. So that gives me 1/12. And then we replace u. So if you are feeling comfortable on these three problems, I would say you're in a really good spot for the test on Thursday. Okay? Maybe you're going to have to go back and look at a couple of these or look at some homework pieces that we have. But the rest of the day today is learning the new pieces. And I'll just tell you, there will be one question on the test Thursday that's long division. So what I'd like you to do is take notes on this, and we're going to title it long division. Now, how do I know when I can use long division? Anytime you have a fraction where the degree in the numerator is greater than or equal to the degree in the denominator. Okay? So when the degree on top is bigger than the one on bottom or equal to it, then we're going to split this fraction up. So I'll give you, well, the first thing we want to think of is, what if I didn't tell you anything about long division and I just gave you this integral? And you're looking at it thinking, okay, I've got a fraction. Don't write this part because I'm going to actually end up erasing it. But what if I decided to let u be the bottom piece right here? Okay? And again, why do we do u substitution? To try to make this an easier problem. Well, we run into a problem when I take the derivative of this, because even though I don't have a 2 present and I move it over, I have an x dx, but I don't have exactly the x dx. I've got more than that. So in this case, u substitution does not work. And that leads us to a problem here with how we approach this. So we need other methods for solving this. And I'm going to call this side work right now. But it brings back something that we've done a long time ago called long division. And actually, I'm going to take the bottom, the denominator, and I want to see how many times does this denominator divide into the numerator. But you're going to notice one thing. See how I put this extra 0x? That's our place filler. We need all the variables from x squared on down to the constant accounted for. So once we set up the long division, remember our goal was to take the value in front and make it look exactly like the first value underneath the divide bar. So what do we got? We're going to times by 1. And when I multiply by 1, you have to multiply all pieces by that value. So I get 1 times x squared, and I get 1 times 0, and I get 1 times 2. And then as we've always done, we add the opposite. So we're going to actually take this and make all these signs opposite signs, and then we're going to add them together. So x squareds go away. I'm left with a negative 4x and a plus 0, but in that case, I'm just not going to write the 0. So what do we have now? Well, I have the factor of 1 goes into this polynomial, plus we have a remainder. And I can't take x squared and make it look like a value less than x squared, so that's why I need to stop here. And what we're going to do is we're going to use long division to rewrite this integral. Well, what was it? It was 1 plus the remainder, oops, I want that in blue, over whatever we divided by, which in this case was x squared plus 2 dx. And the only reason why we did long division was to rewrite the integral so it just looks a little friendlier. All right, now, hopefully you remember, a lot of you, I taught you this in Algebra 2 a couple of years ago. So that's long division. But look at what happens now. Now I can think of this as two separate problems. I'm going to split the 1, and that's a really friendly integral. And I'm going to split this up creatively. You'll notice the one thing that I did here, this 4, the negative 4, is just a multiplier. So we can pull that out because it's just multiplying the whole thing by negative 4, and that makes it less confusing. But now, hopefully you're looking at, wait a minute, I can now do u substitution because this bottom piece, its derivative has an x dx in it. And that's what long division does, is it splits it up and allows us to rewrite the integral so u substitution is potentially possible. I say potentially because it's not always going to work, but almost everything we see will work. So I'm going to let u be x squared plus 2. I'll take the derivative of that. And notice the x dx is present right here. The only thing I don't have is that factor of 2. So I'm just going to move the 2 over to the other side. Now you can see everything in this integral is now replaced by something in terms of u. So the negative 4 is just going to drop down. And I'm going to have the 1/2 du. Well, that 1/2 is a multiplier, so that's going to go out in front. I like to write the du in the bottom, or off at the end. And then we've got u on the bottom. And if the x went away because x dx was taking place of this, there's just a 1 right there. And you can evaluate this integral at any time you want. But notice, now I have a much friendlier integral. And that's the goal of u substitution, is to make this stuff easier to deal with. All right, so let's now finish. Whose derivative gives me 1? It's x. Now, it is x plus c, but I'm not going to put the plus c yet. The reason why is I'm going to have another plus c down here. So c stands for constant, and constant can be anything. So if I have a plus c and a plus c, I'm just going to put plus c at the end. Okay. So then what else do we have? Well, I've got, think of this as negative 4 over 1 times 1/2. That's going to be negative 2. And then the antiderivative of 1 over u is the ln of u plus c. And our final answer then is just replacing whatever u was with x squared plus 2. So long division will make mostly a natural log of u appear as the antiderivative. All right, now that's the first time you saw it. I don't expect you to be an expert at it, but hopefully you were able to follow along. If the long division made sense and you were able to figure out how we rewrote this, that's really the only new part. Everything else we should be super comfortable with. So let's try one more. And I'll give you a little hint here. When the numerator is larger than the denominator, long division allows us to split this up. Okay. I don't write this part, but what if I said, oh, well, what if I want u to be x to the third? And then I take the derivative of that, and then the 3 comes over. Okay, I just want you to be aware of this. Some students see this and think, oh, x squared and dx. I've got a dx there and I've got an x squared here. There's a problem. This x squared is in the denominator. This x squared is positive, so they are not the same, plus the plus 1 kind of screws things up. So in this case, u substitution does not work. So we have to do long division. And again, we just do long division so we can rewrite the integral. So notice I've got x squared and there's a missing x term, so we have to account for that place value. And then here's the tricky part, and you just got to be careful. It is x to the third, but it needs to have all other pieces to it. Okay. So now we're just going to do long division. Right? And again, our goal is to make the first term in this trinomial look exactly like this one, the x to the third. So I'm thinking, what do I multiply x squared by to make it look like x to the third? We times it by x. And even though it's a 0 here, I still want to put 0x times x is 0x squared. And x times 1 is 1x. Now notice these are all positive. So we always think of this as adding the opposite. So I'm going to make them opposite signs. I'm going to use a different color just so that pops a little differently. So I think of adding the opposite. So I just make them opposite signs, and now we'll add. Those go away. X squareds go away because they add up to 0. And then I've got negative 1x plus 1. And that remainder is smaller than the x squared that we started with. So now we're just going to rewrite this. Now what do we do? Remember, x is the first part. That's our answer. X goes into this function evenly, but then there's a remainder of negative 1 over 1 over x squared plus 1 dx. Question said, how come there's a plus 1 under the divide bar? Is it oh, shoot, that's a good question. I don't know why there's a plus 1 right there. I miswrote that. Thank you. This should be a 0 because there's no extra term. I think I don't know what I did there. So that's a 0, which actually means this part is gone. So thank you, Sydney. Appreciate that. Yep, Jonathan, same thing. You guys are on the ball. I appreciate that. So there should have been a 0 here because x to the third doesn't have any constant. And then that just leaves us with the remainder of negative 1x. Okay. So now we rewrite this. And again, if you want to, watch what I'm going to do. I'm just going to put an extra integral here, right? Because I would split this up and say, well, the antiderivative of x is going to be x squared. And if I put a 2 up top, there has to be a 1/2 out in front. So that part is pretty quick. But then when we do this part, now here's what I would do. I don't love this negative 1 here. So I'm going to push the negative 1 out. And then at the same time, I'm going to do u substitution. I'm going to let x squared plus 1. The bottom part is going to be u. So then its derivative is 2x dx. And you'll notice I don't have a 2 present, so the 2 has to move over with the du. But I do have an x dx. So there's my u. The x dx is going to be just this x part because the negative 1 floats out and the dx there. So then I can replace x dx is going to be replaced by the 1/2, but instead of writing the 1/2 up here, I always float that out to the front because that's just a multiplier. I like to write du on the bottom, or out, I shouldn't say the bottom, off to the side. And then what's left is u on the bottom, but everything else was taken away from the top, so there has to be something there, which is a 1. And once you get to this part, the antiderivative is pretty friendly, right? Because the antiderivative is just the natural log of u plus c, and then we get negative 1/2, and the other part drops down. And you actually don't even need to write the u in here. If you realize that we're just going to rewrite u with x squared plus 1, then you could do that right away. You could save yourself a step of work. I don't do that just because I want you guys to see all proper steps. There we go. So you'll notice it's basically the same thing as we did in the other problem. When you have that extra piece with the remainder, it's most likely going to turn into 1 over u, whose antiderivative is the natural log of u, of the absolute value of u. Okay, so that's long division. You will have one of these questions on the test on Thursday. You have 3 of these questions in the homework tonight, so you get to practice some. The other thing we're going to look at is called completing the square. Now, I'm going to show you this, and it's not horrible. It's a little tricky. Actually, I need to grab this. That. So I will ease your mind, though. This completing square will not be on our test. However, it is fair game for the AP test. So we want you to just have this kind of in your back pocket, but know that it's most likely going to be just one multiple choice question if it appears on the AP test. All right, so we got to talk about completing the square. First question I have for you is, do you remember that from Algebra 1 and Algebra 2? Probably not, because most students don't. So let's talk about what we mean by turning the denominator into a perfect square trinomial. Well, what is a perfect square trinomial? It would be something like this. Okay? X squared plus 10x plus 25 is a perfect square trinomial. And the reason why is, how did I get 25? Well, that's 5 times 5. And how did I get 10? 10 was half of the value. If I cut 10 in half, I got 5 and 5. But why is this a perfect square trinomial? Because it can be written as x plus 5 squared. So what about another possible example would be, what if I had something like this, where I have x squared minus 6x plus something. And I want to think of, well, what value here has to be a perfect square number, just like 25 was, that I can split this up into an x plus something and x plus something. Well, the way we do this is look at the middle term and just divide it in 2. Okay? If I take 6 and divide it into 2, I get negative 3 and negative 3. Well, negative 3 times negative 3 would make this a positive 9. And then I could rewrite this as a perfect square of x to x minus 3 squared. So hopefully you have some familiarity with that. Now you'll notice x squared minus 6 is right here. So we know that I need this number to be a 9. Well, what we're going to do is we're going to split this up. We're going to split 18 up as positive 9 plus 9, right? 9 plus 9 is still 18. So if I get creative in this form, I'm going to do two things actually. This 3, I'm going to float to the outside and make it a 1, because that's just a multiplier, right? And if I can have a 1 here, usually that's friendlier. And then I'm going to take that 18, I'm going to rewrite it as 9 plus 9. Okay? Well, that doesn't really change the problem at all. It just changes the appearance. But why can we do that? Well, what if I take that trinomial then and I factor it? Well, we already know what that answer is. We factored it right here. So I'm going to actually rewrite the factored part as x minus 3 squared. And then the extra plus 9 is just off to the side. You might not know it yet, but this is very close to something we already know. So I copied this from the page 439. This is one of our rules. If I can get this antiderivative to look like 1 over 1 plus x squared, or by the way, it doesn't matter if you write the x squared first or last, because it's addition. So we have a value squared coming first, so we're really thinking of it as the x squared is first. The only problem I have is I don't have a 1 here, I have a 9. So now, once you get this and once you do the completing the square and you factor that new trinomial, the number that's left over is what we have to get rid of. Okay, so watch what I do now, and this is a little tricky. I'm going to take every single value and divide it by 9. Why would I do this? Well, 9 over 9 actually ends up being 1. So we're going to get a little creative. It's a little bigger. Okay, now watch what happens. I don't love a 1/9 up top, right? In fact, I need it to be a 1 for the rule. But that 1/9 is a multiplier, so I'm going to just pull the top 1/9 is going to come out. And what's left over then is a 1. We know that 9 over 9 is a 1. And then here's the spot where you really got to pay attention. I can't have an x value squared and then divide by 9. I need that 9 to be in with the x. So watch what happens here. If I take a 9, remember 9 is the same as 3 squared. Well, if the top is squared and the bottom is squared, I can rewrite it as the whole fraction squared and put that 3 inside. So notice, x minus 3 divided by 3 is the exact same thing as x minus 3 squared over 9, because 3 squared is 9. So if you feel comfortable on that piece, now we have everything set up almost perfectly, except for I have more than just an x inside. Well, that's where U substitution comes in. What if I let U equal this whole piece? Then I got 1 over u squared plus 1, which is exactly what we need. The only challenge is you have to think about fractions. I have to take the derivative of this, and I really don't want to do a quotient rule. So I'm just going to divide each piece by its own 3. So think of that as 1/3 x minus 1. And now the derivative is so much easier. It's just 1/3 dx. Now I don't have a 1/3 directly present. You could find one if you wanted to, but I don't recommend it. So all I need to do is move this 3, 1/3, or times by 3, so I'll move it over to the other side. Okay, so we found out what u is, and then by taking the derivative, the dx here is going to be replaced with 3 du. So a couple of things. 3 times 1/9, well, that's 3/9 or 1/3. And then I'm left with 1 over u squared plus 1. And then the dx, this green part, is going to be replaced with a 3 du. But that 3 is a multiplier, so we always write that out front. And then my last spot is, notice, 1 over u squared plus 1. Well, it doesn't matter if it's u or if it's x. Here is the rule. This whole thing is tangent inverse of u based off of the rule plus c. And then you just have to make sure if you do 1/3 times 3, that actually turns into 1, which you don't technically have to write. And then my final answer is replacing whatever we said u was in the start, which was x minus 3 over 3. It's tricky. It takes a while to get used to it. Okay. Let me show you one more example, and I'm going to do this one I don't want you to write it down. I'm going to go through it pretty fast, just so you can see another step-by-step process, and you'll get the hang of it, and you'll see how similar it was to this problem. Okay, so let me do this one really quick. So here's what I have. I have -8. Well, in my head, I'm thinking, I want this to be a perfect square trinomial, so I have to split up 24. Well, I want it to be split up. Well, what plus what gives me -8? It's -4 and -4, so the only thing that this has to be is a positive 16, because then I could write this as -x minus 4 squared. So I want this to be 16 plus 8, which is 24. So then I'm going to rewrite this. The 5 is going to come out in front. I'll rewrite this as x minus 8 plus, instead of writing 24, I'm going to think of it as 16 plus 8. Okay. And then I'm going to group these two, and we already know what that's going to factor out to be. So this trinomial actually turns into x minus 4 squared. And then the only problem I have now is I've got this extra 8. And I don't love that 8 being there, right? I need it to be a 1. So how do we get rid of it? We divide everything by 8. So when I do that, this 1/8 on top is going to come out in front because I want a 1 up top. The 8/8 right here turns into 1. And then I just need to make sure this 8 goes back into the squared value. So I'm thinking, well, what would 8 have to be if I undid a square, and the only thing that we could have is the square root of 8, and that looks a little weird, right? But picture this, if you square the top, you'll get x minus 4 squared. If you square the bottom, you get the square root of 8 squared, which is 8. So that's a little bit of trick. And now we're going to u equal this whole piece. But before I take the derivative of that, I'm going to rewrite it. So I just divided each piece by the square root of 8. So then the derivative is 1 over the square root of 8 dx. And this is a constant. I could care less about it. But I don't have a 1 over square root of 8, so that just has to move over by multiplication. And now I can rewrite 5 times 1/8 is 5/8. And then I get 1 over u squared plus 1. But now remember, the du has an extra square root of 8 in it. And then now this form right here is in the perfect form for the tangent inverse of u. And then I would just think of this as 5 square roots of 8 over 8. And then u, we're going to replace with what we know u originally was equal to. So it takes some getting used to, but it's just one extra little method for being able to use u substitution, and it's just called completing the square. Okay, I know I don't have a lot of time left, so I want to make sure we talk about this. What to expect this week? Well, today you've got homework. I'll show you what that is in just a second. Wednesday, you're going to watch an Edpuzzle video. And then on Thursday, you don't have class. I won't see you, but I'm going to have class with my other hour, and we're going to review for the test. What I'm going to do is post that video afterwards. So if you would like to watch that, you can watch it, and that will give you a little bit of extra help for the Chapter 6 test. On the weekend, the homework is the Chapter 6 Part 2 mini test, and it's due February 28th at 3 o'clock. It's only 7 questions, but one of them is an academic integrity statement, so it's really 4 multiple choice and 2 upload questions. And here's the topics. U substitution with limits, without. There's 1 long division problem, and that's a file upload where you have to show your work. And there's no completing the square on the test. Okay? All of this is on our notes. Your homework tonight then is these 2 sections. The blue ones are completing the square. The red ones are long division. I will be available from 1 to 2 in my office hours. If you have any questions on this material, if you want to talk about 3rd trimester, if you need help paying for the AP exam, please come and talk to me if you have questions. Adios. Have a